We're going to, like I said, we're just going to kind of pick up and finish lecturing here on chapter 2. And again, we'll move experiment 3 to Thursday for sure. We will definitely hit it at that point. So we've been talking really today about electron configuration, orbital diagrams, really how the electrons go into the atom. So, we're going to talk about electron configuration for everybody. We obviously touched upon here as well. We did a bunch of those orbital diagrams. And again, a reminder, if we had something like oxygen, which is the example here, the electrons do go in, as we talked about, one at a time. They have paired spin, which gives them those different quantum numbers as they share those orbitals. And again, based on sort of Hund's rule, as we talked about, the most stable arrangement is to maximize the parallel spins like what we have here, and then go back and really start pairing up those electrons. Oops, in the case of oxygen, we didn't have that many there. Pairing up the electrons in the case of oxygen. And again, as we saw, you could really apply those quantum numbers to a specific electron. So I guess we did like the 17th electron that's there. And again, that's why it's important to know really how the electrons really do populate those orbitals in terms of getting the correct spin and stuff like that. Another important aspect of electrons when we look at electron configuration is there's actually kind of two types of electrons that we sort of come across. So when we look at something like this here for 1s2, 2s2, 2p6, actually get the thing to right there. There we go. In this particular case, what we're really seeing is we basically have these two electrons on the lower energy level. And on the second energy level, it actually has, in this case, 8 electrons happening there on the second energy level. Now, what we classify as valence electrons, which are really important types of electrons, those are the electrons that are the outermost, highest energy electrons. Those are extremely important, the valence electrons, because they are really the ones, because they're highest in energy, they're kind of furthest away from the nucleus, they're really the ones that are involved in bonding. So in the next chapter, when we talk about bonding, we deal a lot, obviously, with the valence electrons. They're also the ones that, as we were talking about earlier, when sort of representative elements gain or lose electrons, that's sort of where they go. We also then have some electrons, which are obviously lower in energy, closer to the nucleus. Those guys are sometimes referred to as core electrons. So core electrons are those guys that are really closer to the nucleus. Again, they're closer to that sort of positive charge of the nucleus, and they're going to be held a lot tighter. So because they're held a lot tighter, they are not released easier. And that's why they are core electrons versus our valence electrons, just for the sake of argument, further away from the nucleus, not held as tightly, and a little bit easier to sort of remove. Also, if you think about those valence electrons on the outside of an atom, when two atoms come together, they're kind of like the first ones to say hello to each other. So that's why we do get that sort of interaction that occurs. So there's a couple different ways that you can basically figure out the number of valence electrons. You could absolutely write the electron configuration for it like we did here. This, by the way, is 10, which is neon. And you could count the ones in the highest numbers, which would be 2 and 6, for a grand total of 8 valence electrons. You could do that for like 1s2, 2s2. That is 4, which is beryllium. And this would be the highest energy electrons. Beryllium would have 2 valence electrons. The much easier way, because nobody wants to write electron configuration for everybody, is actually to look at the periodic table. So when you look at the periodic table, the group number, which is that number that's up on top, equals the number of valence electrons. So everybody in group 1 has 1, everybody in group 2 has 2 valence electrons, 3, 4, 5, 6, 7, and 8. valence electrons, transition metals, as we'll talk about in just a second in this region. But they pretty much equal the group number. So if you look at neon, it's all the way at the end of the periodic table there in group number 8, which is why it has 8 valence electrons. If you look at beryllium, it's sitting right about there, and it's in group number 2, and it has 2 valence electrons. So that's a much easier way to figure out the total number of valence electrons, is just simply going to the periodic table and looking at the group number. In addition, the periodic table can be very helpful with electron configuration. But while we're here, let's just talk about a couple of things about the periodic table, and we'll talk a little bit more in just a second. When we talk about groups, those are things that go up and down, and we typically use the representative numbering when we are looking at a periodic table. If you look at a periodic table, you'll sometimes see A numbering, you'll sometimes see B numbering as well. We use the A numbering, so when we talk about group 1, this is group 1 here. It actually starts with this guy, which is lithium. This is hydrogen, by the way. But group 1 actually starts with lithium, even though hydrogen is sitting on top of it. This is group 2. We skip the middle part, and then this would be obviously group 3, 4, 5, 6, 7, and 8. And again, most of the time people don't say 8A or 7A. They just say group 7 or group 8. They usually leave the A out. And that's our neon we were just talking about, which is member of group 8, has the 8 valence electrons. And again, our beryllium, which is like right there, member of group 2, has 2 valence electrons. So that's a nice, easy way to figure out the number of valence electrons. We also will see period numbers on a periodic table. So groups kind of go this way. Periods go this way, as we will see a little bit later on. And these period numbers go from 1 to 7, which, if you remember, our good friend, our quantum number, goes from 1 to 7. And that's really what these numbers would represent, which means if you really sort of know what you're doing, you can essentially count off electron configuration from the periodic table. I don't know if I recommend doing it. If you're not 100% sure, I would use the zigzag thing that we were just talking about. But just to kind of show you sort of what's happening, as you can see here, the blue on the left, the first 2 groups, that was referred to as the S block on the periodic table. S's have a grand total of 2 electrons, 1 S electron there, 2 S electrons there. Group 3 to 8, kind of the yellowish color here on the screen, that is what is sometimes referred to as the P block over here. P subshell can hold 6 electrons. That's P1, P2, P3, P4, P5, and P6 going that way. Down here is the D block. D block is 10 electrons. That would be D1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And on the very bottom is the F block down here. And F block has 14. So like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14 electrons. So you literally can sort of count off electron configuration from the periodic table. And again, to kind of show you how that would work, just erase a couple of things here so we can see. And let's just say we'll do one that we did earlier. I think we did sodium earlier, which is right here, I believe. So this is sodium. So if you were to sort of count electron configuration from the periodic table, and we'll go with that one. Actually, maybe we'll go with this one here. You would start at the top, and this would be 1s1 all the way over to here, which would be 1s2. You then go to the second energy level. This would be 2s2 to there. This would be 2p6 to there. And then coming here, this is 3s1. So just like we saw earlier, sodium would be 1s2, 2s2, 2p6, 3s1. Now, if we looked at, say, something like chlorine, which is like right about here, I believe. That's about chlorine. We could do the same thing. Chlorine, which again has 17 electrons, 1s2, 2s2, 2p6, 3s2, 3p5. So again, how we would count that off, starting up here on top, 1s1 to 1s2 over here to helium, coming back 2s2 all the way across here, 2p6, 3s2, and then jumping across here, 3p1, 3p2, 3p3, 3p4, and 3p5. So again, you can really use the periodic table to help you with electron configuration. I would again probably recommend you do that zigzag thing that we were using, because there are problems in places where you can go wrong if you don't truly understand what's happening. So for example, I think we also looked at iron earlier, and iron was somewhere around here, I think. And iron again had 26, which was again 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. So same counting, 1s2 to the end here, 2s2 here, 2p all the way across here, 6, 3s2 here, 3p6 all the way to the end, 4s2. Now, if you're not sure what comes next, this is not 4D. This is actually 3D, because the d orbitals start at the third energy level. So even though it's on the fourth period, that is 3D. This is actually 4D, 5D, and 6D. So the Ds are one behind the period number here. And that's why you got to be careful and remember that, so you don't think it's like 4D at this point. So this would be 3D1, 3D2, 3D3, 3D4, 3D5, and 3D6. So, there is some areas, if you're not 100% sure what's going on, you might get the wrong one. And that's for sure. The D block is always one behind the period number. Question on that? In addition, if you actually look at a periodic table, we'll see another picture a little bit later on, as these arrows imply, this is actually goes right here. That's where that first row goes, and the second row technically goes right here, and that's on period 6 and 7. But these are the F blocks, and if you remember, F start at 4F, and this would be 5F. These guys are actually 2 behind the period number. So this is why I say probably for most people, using the zigzag approach like we did earlier is probably the best way to go, especially if you're getting into some guys in the transition metal region or down here. If you're not very careful and you're trying to count things off on the periodic table, you might actually get sort of the wrong configuration. But if you know sort of what you're doing, where the D starts and where the sort of F starts, you really can sort of probably figure it out. Any questions on that there? All right, so why don't you do these configurations here? Let's do sulfur, barium, and let's do chlorine. I want to do barium. Barium is way down there. I will do barium. Why not? All right, take a second and do barium. See what you come up with. or not barium, do them all. And see what you get. Just in case you're not sure, don't have a periodic table, sulfur is number 16 on the periodic table, barium is number 56, and chlorine is number 17 on the periodic table. S2, 2s2, 2p6, again following the zigzag approach. After that, you would come back to 3s2, and at that point, we're going to sulfur there. So that would be 3p4, looks like. Again, if you want to do more of the noble gas configuration, we would back it up to the noble gas that comes before it, which would be this 10 right here. So then we would have neon, 3s2, 3p4 in that case. Any question on that particular one? Then we go with barium, which is 56. I'm regretting that already. So we go 1s2, 2s2, 2p6, 3s2, 3p6, again 4s2 at that point. That's like 20 if I'm not mistaken, almost there. We got to then go to our 3d10 would be next, followed by our 4p6 at that point. And then we would go to 5s2 next, followed by 4d10, and that would then be followed by 5p6, and gosh, I hope I'm almost there. And then we got 6s2. I'm going to hope that's 56 there. So that's what do we have there? 20, 30, 36, 46, 46, and 6 is 52. So I think we're there at that point, I believe. We also could just go with xenon, which is 54, which should take us to about here, and then finish it up with 6s2. Any questions on that particular one there? Okay. Lastly, kind of like the first one, is 17, 1s2, 2s2, 2p6, 3s2, 3p5 on that. You could also shorthand it the same way as the first one, neon, 3s2, 3p5. Any questions on how to, again, write regular configuration here or the noble gas configuration? Okay, so we sort of touched upon it at the end of lecture, but let's talk a little bit more about the transition metals and sort of what happens with electron configuration with those guys. And again, the transition metals on the periodic table, if we look at it, and again, we'll see it in just a bit as well, is there's group 1, group 2. So this is our transition metals here. And then 3, 4, 5, 6, 7, 8. So that sort of area in here is our transition metals. And again, they are slightly different because of sort of how close they are, those orbitals. So as we were talking about at the very end, as the electrons go in, again, that 4s is lower in energy than 3d. But as they do get filled, we do get that switch in energy that occurs. And as we just talked about at the end as well, that's how come when they do lose electrons, those transition metals will always lose those s electrons first. So they're always, and man, this is our s block. So when transition metals start to lose electrons, they actually will lose those first. And if they need to, then they'll start to lose those d electrons. And when they actually do lose electrons to get something with a charge. So the example that I did there at the end was iron. And again, iron, which has 26. And as we just sort of did, that would be argon, 4s2 and 3d6. Again, when it makes a +2 charge, it means it lost 2 electrons. So it would go to 24. Again, even though they go into the S first because they're lower in energy, because there is that switch that occurs between these two, those 2 electrons would be the ones that would be sacrificed, and it would be argon 3d6. If we went to iron with a +3, that means it actually has 23 electrons. And the same thing would happen here if we look at just iron's configuration with no charge. They would also lose those 2 electrons first, but in this case, it actually needs to lose 3 electrons. So the next sort of highest in energy would actually be an electron out of here. And what would end up happening is we would end up with argon 3d5. So transition metals, always when they make positive charges, they actually will lose those S electrons first. They then will dig into those D electrons and lose them. They are also different than representative metals. So representative metals, which are the guys in group 1 and 2, like sodium, magnesium that we talked about. When those representative metals in group 1 or 2 lose electrons, they back up to the noble gases. When transition metals lose electrons, they actually don't back up to noble gases. So they don't actually reach that noble gas configuration by losing electrons normally. And so that's a slight difference as well between sort of a representative metal that's found in group 1 and 2 on the periodic table, even aluminum over here, group 3. All those metals, when they lose electrons, they always back up to the noble gas that comes before them. But because of the transition metals, they typically don't lose enough electrons to reach back to a noble gas. Any questions on that there? So why don't you try one here with a charge just to make sure. Let's say we had chromium, and normal chromium is 24 electrons. Let's say we had a chromium that had a +4 charge. What is the electron configuration for that guy? So take a moment and write the electron configuration for chromium with a +4 charge. Okay, so let's talk about this one here. Actually, a pretty bad example. I meant to actually say nickel, but I did chromium. So let's actually talk about chromium. Chromium, and another kind of unusual thing that occurs with transition metals is there are certain electron configurations that are not what you would expect it to be. So when we do our sort of zigzag approach there for electron configuration, we might think a configuration will come out one way, but there are certain transition metals that actually doesn't sort of occur that way. And it really is because of this situation here. Because these orbitals are really close to one another, they're able to sort of allow electrons to sort of move from one energy level to the next. And experimentally, it's been found, for example, that chromium actually is one of those exceptions. So if we did chromium like we normally would with the zigzag guy, we would end up with something like 1s2, 2s2, 2p6, 3s2, 3p6, and then you would go 4s2 and 3d4. And again, if you follow that zigzag guide, that's probably what you would end up with. And what has been found sort of experimentally is there's actually an exception, and chromium is one of them. And what ends up happening is chromium is actually a lot more stable when there's actually an extra electron up in the d orbitals. And the real configuration is this exception. And the main difference is it happens at the very end there. So it ends up being 4s1, one less electron in the s, and one more electron there in the d, which is what we see here again in terms of its configuration. Copper, which is number 29, is the exact same exception. Again, it has one more electron in the d orbital than it does in the s orbital. And again, because they're so close to each other, it doesn't take a lot for one of those electrons just to find its way up into the D sort of orbitals. What does that actually do? You know, you think about sort of Hund's rule, and maximum stability is when we sort of parallel out our spins. So when we add sort of that extra electron up there in the D orbital, we are maximizing our parallel spin. And the same sort of idea, you know, if we have that extra one kind of up there, we are sort of maximizing our parallel spin with this guy, which is technically higher in energy in terms of copper. So those are two very common exceptions to sort of the normal electron configuration. And you do need to know these exceptions. So yeah, so you do need to know these two exceptions for sure, chromium, copper. We're going to see a few more exceptions on the periodic table, but definitely these two, you should definitely know the exceptions of how they're written, and that's how you should write it. So back to my sort of bad question of, you know, what happens when we get a +4 charge. At this point, this would be our correct sort of configuration for chromium, which means when it does lose an electron, 4 of them, again, it would have 20 electrons at that point. The first electron that would be lost would be this electron here. At that point, it would then need to come into here, and we would need to lose another 3 electrons out of here. And what we would end up with is argon 3d2 would be the proper configuration. Again, losing those s electrons first, followed by some d electrons. Question on that particular one. Again, I was thinking about nickel 4, and just to give you an idea on that, nickel with no charge is 28 electrons. With the +4 charge gets us to 24 electrons, which again means that we would end up with argon. And normally, again, nickel is argon 4s2, 3d8. So losing those 2 electrons and another 2 out of here would leave us 3d6. So again, this is really specific for transition metals. They definitely always lose those S's first, followed by, like I said, going into the D's if necessary. Again, 2 exceptions, chromium and copper with no charge. That is the configuration. And if you also look on the periodic table below copper and chromium, things like silver and stuff, you know, there's more exceptions, as we will see here on some other slides. This is sort of what we just talked about. Here are some more exceptions to what we normally would expect to find with electron configuration and what has sort of been found experimentally. So again, for our class, these are the 2 that you definitely need to know. But again, we do see some other exceptions. And if you kind of look on the periodic table, these guys are kind of below chromium and copper. Also, silver is an exception, just so you know. You even have some like here with PD, actually has no electrons in the S. They both have been basically upgraded to the d orbitals in that particular case. So there is actually a lot of exceptions, especially, like I said, if you look at the periodic table where chromium and copper is, pretty much everybody kind of below it, you know, there's a lot of these sort of exceptions to the normal electron configuration. But again, for our class and probably most classes that you do, these are really the 2 that you should know for sure. And for anything else here, you could write it based off of that zigzag arrow thing that we've been using, even though technically it may not be 100% correct, because again, in that transition metal region, there is a lot of exceptions. Any questions on that? Okay, so now that we sort of touched on the periodic table as well, let us talk about the periodic table. I hope, where is that periodic table? Get that here, see that, there we go. Okay, so let's talk about the periodic table. As I mentioned before, obviously the periodic table is an arrangement of the elements. When we talk about the periodic table, as I mentioned before, groups. If you're old like me, sometimes people used to call them families, but not so much anymore. But most of the time we talk about groups. And as I mentioned before, we do use that representative numbering for groups. And again, this is group 1. And again, group 1 does start with lithium, even though hydrogen is hanging out on most periodic tables right there. We skip the middle part here. These are our transition metals, as we've been talking about. And then group 3, 4, 5, 6, 7, and 8 here. Also, as we talked about earlier, that's period 1, 2, 3, 4, 5, 6, and 7. So a period, again, a group is up and down. A period is left to right there on the periodic table. And some other important things, as we know, inside the box. Inside the box there, we have the number up on top, which is the atomic number. And again, that is our number of protons. We also usually will have like a number on the bottom as well. That is the atomic mass. Again, not the mass number, but that is the atomic mass that you find on the periodic table. When we look at the periodic table, as you can see on this chart here, it is kind of broken up into basically 3 categories. We have metals, non-metals, and metalloids, or semi-metals. So metals, usually on most sort of periodic tables, you see kind of like this staircase that's coming down, as you can kind of see with the blue there. And really to the left of the staircase there, those are where we find our metals, including these guys down here. Those are all metals, and metals are very good conductors of heat and electricity. So good conductors, heat and electricity. They usually can be hammered into sheets. They can be pulled into wires. They typically have a shiny appearance. For the most part, all metals are solid at room temperature, except for our good friend mercury, which is a liquid. So mercury is somewhere in this ballpark, right about there. And a lot of times on periodic tables, you could kind of, it's maybe a different color or something like that. Now, nonmetals, on the other hand, are pretty much like the opposite. Nonmetals, which are obviously found over here, kind of to the right and up of the staircase. Nonmetals pretty much are dull and brittle. Not very good conductors of heat and electricity. They also have a much varied state. So some nonmetals like nitrogen, oxygen, chlorine, those are gases. Things like bromine is a liquid. Things like carbon and sulfur, these guys are solids. So kind of unlike metals, nonmetals do have a little bit more variety in terms of sort of their states. Also, our nonmetals is where we find a lot of our diatomic molecules. Diatomic molecules basically means that there are 2 atoms there, and that is nitrogen, oxygen, hydrogen, chlorine, fluorine, iodide, bromine. These are all diatomic molecules because they're basically 2 atoms together, but they're also all elements. And this is how, you know, hydrogen uncombined comes by itself. It comes as hydrogen gas. Oxygen by itself comes as O2 uncombined when it's by itself. also why when we talk about group 1 that it starts with lithium, because if you look at the color here where hydrogen is actually a nonmetal. Even though it's hanging out over here on the left-hand side with our metals, it's actually a nonmetal. Years ago, you would often very commonly see hydrogen found on both sides of the periodic table. And that's because really hydrogen is a nonmetal, but it does have a lot of weird properties that makes it behave sometimes like a metal, but it technically is a nonmetal. So that's why when we talk about group 1 starting, it does start with lithium and not hydrogen, even though you'll find it on, most periodic tables right above it. In addition, there's this sort of staircase. This is boron. Some books include it, some don't, but this sort of step down here. These guys are metalloids, and they're sometimes called semi-metals as well. And metalloids or semi-metals, they pretty much have properties that fall between metals and non-metals, which makes sense based on their location. They're kind of at that point where we go from metals up to non-metals. So if you took just like one semi-metal by itself or a metalloid, that particular element would have properties that are sometimes very similar to what you would see in metals. And that same element would also have properties that are very similar to what you would see in non-metals. So kind of like a dividing line between metals and non-metals. These guys as well, if you look at the periodic table, and again, if you follow the numbering right about here, this is 55, 56 in terms of the atomic number. This is 57. And then we kind of jump to 73 right about there. But if you follow the numbers down here, this guy is like 58. And if you follow the numbers underneath there, that's like 87, 88, and then we have 89, and then we jump to 104. This 57 is lanthanide here, La. This guy right here is our actinide. And that's why these are called the lanthanides and actinides, because technically speaking, these two guys actually go right in here. And those two guys actually would fit in there, but they're usually not put in there very often. They're usually put on the bottom, but that technically is sort of where they would fit into the periodic table if you put them into the periodic table. So those are metals. They're usually set aside again, so your periodic table is not 40 feet wide with those guys in there. I've only seen one periodic table ever where they were actually in the right spot, but it did sort of spread out the periodic table. It covered an entire wall because they had to spread it out over everything. In addition, there are certain groups that have certain names, so groups that have special names. Starting in group 1, which again is our lithium and down, that is what is known as the alkali metals. Right next door is group number 2. Right here, we have beryllium, magnesium, and so forth. That is our alkaline earth metals. And one thing that we typically see out of group 1 and group 2, if you're not sure what the term alkaline means, it pretty much means basic. And that's where we find a lot of strong bases come from, like sodium hydroxide, potassium hydroxide. They pretty much come from group 1 and group 2 off the periodic table. And again, that's why they're referred to as really alkaline earth metals and alkali metals. They're kind of basic in nature. In addition, if we go to group 7 over here, group 7, which is our fluorine, chlorine, bromine, iodine, and so forth. These are our diatomic guys. These are our halogens, group 7. So group 7 are halogens. And again, these guys do come pretty much as 2s, and that is how they naturally come. If they're by themselves, they pretty much come as those 2s. Lastly here, group 8. Group 8 is where we find our noble gases. They're sometimes referred to as rare gases. Not so much anymore, but years ago. They're usually referred to now as noble gases. So that's our helium, our neon, our argon, our krypton, all of our ons, our xenon, our radon, all that kind of stuff. So group 8 is our noble gases. They are chemically inert, which basically means they're very unreactive. They'll react with themselves, but pretty much nobody else. And they're also really what everybody strives to be. Everybody strives to be like the noble gases, as we'll talk about in the next chapter in terms of bonding. That's essentially what everybody really tries to get to in terms of their electron configuration. In addition, as I mentioned before, we have our transition metals that are here. So these guys on the bottom are sometimes referred to as inner transition metals. Again, they're referred to as inner transition metals because, as we just talked about, they technically kind of go up in this area as well. Any questions on the periodic table? Obviously, you need to know periodic table. You need to know where you find metals, where you find nonmetals, where you find metalloids. You need to know where the transition metals are. You need to know where group 1, group 2, 3, 4, 5, 6, 7, 8 is. You need to know the special names of group 1, 2, 7, and 8. Any questions on the periodic table? Okay. So now that we kind of talked about the periodic table, let's talk about, hopefully, let's talk about actually periodic trends and sort of what's going on with, periodic trends, why we see certain things that occur. So there's really sort of 3 major sort of trends that we're going to talk about. We're actually going to add one more, which is actually electronegativity. And this is actually out of chapter 3, electronegativity. So that's the only thing from exam 1 out of chapter 3 that you have to worry about is that guy there. And we're going to talk about ionization energy. We're going to talk about electron affinity and the atomic radius and electronegativity and sort of what happens on our sort of periodic trend. So let us start with also an idea that is sometimes what is referred to as effective nuclear charge. So something known as effective nuclear charge, sometimes referred to as Z effective. And it's really sort of the phenomenon that occurs when we have a lot of electrons and they're near the nucleus, and there's other ones that aren't so near the nucleus. So for example, let us think about a nucleus that has a +3 charge, right? And it maybe has 2 electrons. So it's got an electron here on one energy level. It's got an electron on a higher energy level. Again, 1s2, 2s1. By the way, we're talking about lithium here. So this is our valence electron, as we talked about. These are our core electrons, which are closer to the nucleus. So when we talk about our core electrons, these 2 electrons here, they are basically filling the full brunt of that positive charge. And one thing about positive and negative charges is obviously they are attracted to each other, but the attraction gets even greater when the charges get larger. So if you have something that's like +3 and -3, it's going to be a much higher attraction than something that is, say, +1, -1. So with those electrons there filling that really big positive charge, the full brunt of the positive charge, there's going to be a very strong attraction between these 2 electrons. And that's why those 2 are really our core electrons here. That's why they're pretty much not going to go anywhere because, they're pretty much held in there very, very tightly. But what happens to our sort of third electron here, which is our valence electron, is that electron is actually experiencing something which is referred to as shielding. And what does that mean? Well, it means that it's got these two electrons kind of in the way of it feeling that full force of that +3 charge. They're basically blocking a lot of that positive charge. And what that ends up doing to that valence electron, this guy out here, is instead of feeling the full force of that positive charge, you could calculate something like the effective nuclear charge is feeling. It is the positive charge of the nucleus plus how many electrons are in front of that electron. So in this case, there's 2 electrons. Electrons are negatively charged. So essentially what we're calculating here is because of those 2 electrons that are in front of the +3 nucleus, this outer electron is actually only feeling like a +1 attraction, which means it's not really going to pull itself in as far. It's not going to be held as tightly. And that's why that valence electron is able to be lost or shared and stuff like that much easier than our core electrons that are much, much closer to the nucleus. So the effective nuclear charge is an important sort of element in the trends that we see on the periodic table, and why, certain electrons are easier removed, while as we get into, say, core electrons, because they're so close to the nucleus, they're really feeling that full brunt of that positive charge. And it's going to basically hold them there pretty tightly. It's also going to kind of move them all in as well, a lot tighter. So the bigger that positive charge, everything gets kind of sucked in closer to the nucleus. And the overall size, for example, of everybody kind of shrinks as well. Any questions on that there? Okay, let's see. I think that's probably good for tonight, especially since we took a quiz and everything. So I think we'll lay it up there. We definitely will finish chapter 2 during lecture on Thursday, provided no technical issues, and we will roll into chapter 3. And like I said, at that point, we should have finished, we'll be able to finish the rest of these trends, which will relate to experiment 3, which we will do on Thursday as well. And we'll talk about the study